All right, so we'll look at the second part of vectors. And remember, we are going to try to get away from sketching. Okay, we'll do sketching if we have a word problem. That'll be a good use for sketches. But if we don't, we're going to try to solve what we can more numerically. Yes?
Are there going to be sketches on the test?
They'll be similar to the homework where you have to look at a picture and identify like if it's true or false kind of thing.
Okay.
So it's more like you'll be given a sketch and you've got to determine something from it. Yeah. All right, so this is the second way we learned how to write vectors yesterday. It's not graphical. It's where you just write down the components. The first number represents which component of the vector? Yep. The horizontal. And the second number? Yep.
Vertical.
The vertical. Yep. So if you have two vectors, they would be equal to each other when the horizontal components are the same and the vertical components are the same. So what that means is when you draw them, they don't necessarily have to be in the same spot. Right? They don't have to have the same initial and terminal points. So take that grid. If I have a vector that starts here and goes right 2 and up 3, and then I draw another vector over here that goes right 2 and up 3. Even though those two vectors don't have the same initial point or the same terminal point, they are the same vector. Okay? Two vectors being equal does not mean they're drawn in the same spot. It means they have the same components. Right 2, up 3. Right 2, up 3. Any question on that idea? How about if I drew this vector? Is that vector the same as the other two? No. The components are different. This vector is left 2, down 3. Okay, so that's different. What is the same, though, between this vector and that vector? Yep. They do have the same magnitude, yeah. They have the same length, but they're definitely not the same vector because the direction is different. All right, so the last notation we're going to look at for writing vectors is what's called unit vector notation. Okay, this is the one that is used most often when you want to write down a vector and you don't want to draw it. So first, reminder what a unit vector is. What did we say yesterday a unit vector is? Yep.
Has a magnitude equal to 1.
Right, it has a magnitude equal to 1. So we're going to look at two special vectors that have a length of 1. And the first vector we're going to look at is called I. Okay, so that's a bold I. And the vector I is a special name for a vector. So anytime you want to name a vector, you can pick a letter, but don't pick I. So I is the vector that is 1 unit long, and it points to the right. There's a picture of I. That's exactly what I looks like. 1 unit long, and it points to the right. Okay, so that vector has a special name. And there's one other vector that has a special name. Can you just wait for one person?
This is
She should be right back. So vector I, 1 unit long, and it points right. The other special vector is J. Oh, yeah, sorry, you can go ahead. I was saying J. Did you sign up? So vector J is 1 unit long, and it points up. So if you have to pick a name for a vector, don't pick J either. because j is something special. And the vector j looks just like that. It's 1 unit long, and it points up. Okay. Any question about what I and j look like? So the idea is what we're going to do is we're going to take those I and j's and we're going to stack them together to kind of build whatever vector we want. So think of i's and j's as building blocks, and we'll connect them, as many as we need, to build whatever vector we want to build. And if we need to use a half of an I, we can do that. Or we can use, a third of a j. We can use parts of I and j. So let's look at how we could build the vector 3, 4 using i's and j's. So what we're doing is writing the unit vector notation. Let's start by making a picture. Remember, that notation doesn't tell me where to start, so I can start anywhere I want in the grid. I'm just using it as a grid. I'm not starting in any special spot. And how many units am I going to go horizontally? Yep. 3. And which way?
To the right.
3 to the right. And how many units vertically?
3 to the right.
So we got 3 to the right and
It'll be 4 up.
4 up. Okay. So we're going to go 3 to the right and 4 up. So that is a picture of the vector that we're going to build. I've made a copy of I and j, and what I want to do is stack these i's and j's together, starting at the initial point and ending at the terminal point. How many of the i's am I going to need to start to go from here up to there?
3.
Yeah.
No, 3.
3 of them. So I'm going to make 3 copies of the i's. Okay, I'm going to stack 3 of those together. 1, 2, and 3. So what do you think we would call this bottom vector that I just drew in purple? Yeah?
3i.
3i. Yep. So we have 3 of the i's plus how many of the j vectors am I going to need? And I'm just going to draw them by hand rather than copy and paste it. I'm going to need 4 of them. So I'm going to need 1, 2, 3, 4. Okay. And what vector did I just build in purple? Yep. 4j. And that is what we call the unit vector format. You're just explaining how many i's and j's you needed to stack together to build your vector. So now if you were to connect where you started to where you finished, this is kind of like what we did yesterday. We'd go from here to there, which is exactly the vector we were trying to build. 3i plus 4j. Now, if we just use I and j, we can basically travel right and up. But what if I wanted to build excuse me. Thank you. What if I wanted to build that vector? That's not right and up. What would I need to do in this case? Yep.
Use negatives.
Yeah, I would need a negative. In this case, it would be negative 1i. We'd need 1 to the left, and we'd still need 2 of the j's going up. So this would be negative I plus 2 j's. So using the I and the j and the negatives, we can go in any direction we need to, up, down, left, or right. So that means we can represent any vector we have to in 2 dimensions. If you needed to build a vector that did something like this, that's fine. We could do one of the i's, and then we'd need a j, and then half of j. So 1i plus 1.5j, 1.5j. Any questions on that? When we get into 3D, we're going to need one more unit vector to be able to build things. I allows us to move on the x-axis, j on the y-axis, and then anybody have a guess what the 3rd unit vector is going to be called in 3D? Yeah? No, not u. Yep.
K.
K. Yep, I, J, K. So K would be the 3rd vector we would need, and that's going to allow us to move on the z-axis. That would be like out of the board and into the board. All right, let's look at some formulas for vectors. Okay, in the formulas that I'm about to write down, V, again, that's bold, and W represent vectors. Alpha is going to represent a scalar. So remember, 3 things that a scalar can do. What happens when you scale a vector? It could get longer or shorter. And one more thing, besides longer and shorter. Yep.
Reverses direction.
You could reverse direction, and how would that happen?
Negative.
If you multiply by a negative. Yep. Okay. So here's our 2 vectors. And I'm going to use both formats we know interchangeably. This is the format we learned yesterday. They call that algebraic notation. And the i's and j's, they call it unit vector notation. Okay. If we want to add 2 vectors together, instead of drawing the first vector, like that, and then putting the second vector on the end, and then drawing in the diagonal, instead, all we're going to do now is add numbers. We're not going to draw pictures. To add 2 vectors together, take the horizontal component in the first vector, take the horizontal component in the second vector, and add the 2 together. Take the vertical component from the first, from the second, and add the 2 together. So this formula is going to take the place of doing something like this. We're not going to have to do that now. Now, if we wanted to subtract 2 vectors, we would take the first one, flip the second one around, and then put it on the end. That's a picture. What do you think is going to be my formula to subtract 2 vectors without using a picture? Yep.
Y minus y, or x minus x.
Yeah, we're just going to subtract the components. So if you want to subtract 2 vectors, you have to do it in the order that they give it to you. So v minus w. Take the horizontal from v and subtract the horizontal from the second one, which I call w. And same thing for the verticals. Okay, so that takes the place of having to do a sketch. Yesterday we called this a certain kind of product. Anybody remember what we called this? Yep. Scalar product. When you want to do a scalar product, normally what you do, like if you wanted 3v, you take one of the v's, make 3 copies of it, and then draw your answer. Okay, that's a visual, stacking them together. All we have to do to scale a vector, think of it as like a distributive property with the scalar. Take the number that you're scaling by and multiply it to each component. Multiply the horizontal component by the scalar and multiply the vertical component by the scalar. And if we distribute that out, that's going to take the place of having to draw it. Okay, and the last formula is for that. What does that mean? We put a vector inside those double bars. Yeah?
Isn't that magnitude?
That's magnitude. And what does magnitude mean? It's the, like a simple word, length. Right? It's the length of the vector. Well, let's go back to this picture. Let's say I want the length of that vector that I just drew in green. Well, you can't count the boxes because it's slanted. Right? If it was perfectly horizontal, then you could count 1, 2, 3. But anyone have a guess how we're going to find the length of that vector that's in green? Yeah.
Would we try to find like the slope of it?
We could try to find the slope. That wouldn't directly tell us how long it is, though. But it kind of would tell us something else that might be useful. Yeah?
Do you take the coordinates of the initial and then at the final point, or like subtract the final point from the initial?
You could do something with subtraction to kind of get at what I'm thinking you need. You could do something with subtraction, yeah?
Does it have to do with x2 minus x1?
Yes. Yeah.
Could you try to find like the hypotenuse triangle?
How would you find the hypotenuse?
Because you have the two sides, and now you have the and obviously making the right triangle because it's
So if you knew the two sides, though, what does that do for you? How does that give you the hypotenuse?
like you have to find the hypotenuse.
How?
I'm blanking.
Pythagorean theorem. So when you want to find the length or the magnitude of a vector, what it's going to come down to is finding the length of the hypotenuse in a triangle. This side's 3, that side's 4. So if you did Pythagorean theorem on that problem, you would get 5. So the way we're going to do it is you're going to square this number, you're going to square that number, add them up, and then take the square root. So that's the Pythagorean theorem. And that's what I have written right there. Square the horizontal component, square the vertical component, add them together, and then take the square root. So if you look at all 4 calculations I just showed you, adding, subtracting, scaling, and magnitude, which one out of the 4 is the final answer very different than the other 3? Magnitude. Magnitude, when you find the answer, is a single number. 12, 13, 16.5, whatever it comes out to. But all these other ones are vectors. When you add, subtract, or scale a vector, the answer is a new vector. When you find the magnitude of a vector, the answer is a number, just a number. Okay. Any questions on those 4 formulas?
Which one was which?
Well, the top one is add, then subtract. The third one is scaling, and the fourth one is finding magnitude. All right, so now let's try it on a couple of vectors. So I've given you 2 vectors in both unit and algebraic notation. And the first thing I want to do is add them up. Okay, if you were to add the v and the w together in this case, what would you get in the unit vector notation?
Question, please.
So if you were to add these 2 vectors together, how would you write your answer in unit vector notation? Yeah?
I Are you looking for like a final answer?
Yep, in unit vector notation.
Okay, so without any plus or minuses? Or do you want plus
Well,
minuses?
unit vector notation, so it probably needs a plus or a minus.
Okay. Wouldn't it be 2 plus 3, comma, 3 minus 4?
There's no commas in unit vector notation.
Oh, okay.
We'll talk about that other notation in just a minute.
Okay.
Hang on to that. Yep.
Is that 5i minus j?
That's 5i minus, you could say minus 1j, or you could just say minus j. That is unit vector notation. Has to have i's and j's in it. Now, that's the same as, what did you say when you gave me the other notation?
2 plus 3, comma, or, yeah, 2 plus 3,
Which is
5,
5,
and then comma, and it'll come out to be -1.
-1. That's the same thing. Unit vector notation, algebraic notation. That's just what our book calls the second one. All right, let's try v minus w. All right. What would v minus w be in unit vector notation? So again, no sketch. We're not going to take the second vector w and flip it around and put it on the end. That's what we did yesterday. Today it's just numeric. Yep.
Is it -I plus 7j?
Yep. -I plus 7j. 2i minus 3i, and 3j minus -4j. And what would that be in our other notation? Yep.
-1, 7.
-1, 7. Yep. Okay, so that's adding and subtracting two vectors. Okay, let's try scalar. So yesterday we would have taken v and we would have made 3 copies of it and connected them all. And that would have been our answer. But today we're just going to scale v. What would 3v be in unit vector notation? Yeah.
6i plus 9j.
6i plus 9j. So think of that 3 as being distributed to each number in the vector. Distributed to the 2 and the 3. So 6i plus 9j. Or in the other notation, we would write, yeah,
6, 9.
6, 9. So 6, make sure we put it in those angle brackets, because if you put parentheses, that's a coordinate, not a vector. And the last one, magnitude of v. Okay, so before we write the final answer, I want to make sure we write down the formula with the numbers in our vector filled in. So we've got the vector 2, 3. Okay. How would you write down your calculation to find the magnitude of v?
2 squared plus 3 squared, and then the square root of whatever that number is.
Yep. So the square root of 2 squared plus 3 squared.
Yeah, 13.
So that's going to be 4 plus 9, which is 13. And if they want an exact answer, we're done. Square root of 13. And what theorem did we just use? Right, we usually just used the Pythagorean theorem, and we had a side of 2 and a side of 3. We just found the hypotenuse. Right, so any question on adding, subtracting, scaling, or finding the magnitude, all without any sketches? So remember, this is something we said yesterday. If you have a vector that is exactly 1 unit long, then that is called a unit vector. And we do have two special unit vectors. I points right, j points up. What I want to know is if I give you a vector that's not a unit vector, I want you to be able to take and turn it into a unit vector. I don't want you to change the direction. I just want, let's say this red vector is a unit vector and the black one is not. I would want you to take this black one and be able to scale it down until you turn it into a unit vector. So you're changing the length of the vector that I give you until you get it to be exactly 1. Okay. And there's a pattern to what you need to scale the vector by to do that. So let's say that you had a vector, let's say that the magnitude of your vector was 5. What would you have to scale a vector that was 5 units long by to make it exactly 1 unit long? Yeah?
I mean,
Yep. 1/5. Okay. So what we're doing is we're just going to make a table that if I give you a vector, what you scale it by to turn it into something that is 1 unit long. We're not changing the direction. We're just making it 1 unit long. What if you had a vector that had a magnitude of 8? What would you scale it by to make it 1 unit long? Yeah, you'd scale it by 1/8. What if you had a vector that was 1/3 of a unit? What would you have to scale that by to make it 1 unit? Yep, 3. So in that case, the vector was too short. We had to make it 3 times longer. And then it turned it into a vector that had a length of 1. Well, let's say we had a vector that had a length of x. What would you scale it by to make it exactly 1 unit long? Nico?
1/x.
1/x. Yeah. So basically the pattern is if you take a vector and you scale it by the reciprocal of its magnitude, that means take its magnitude and flip it, and you scale it by that number, you will turn it into a unit vector. Okay, let's write that down. Okay, so this is just explaining what we're doing. We're finding a new vector that points the same way, but it's only 1 unit long. And the formula, let's think of it like, I don't know, this. So the pattern is to scale the vector by its magnitude flipped, and that turns it into a vector 1 unit long. So let's say we had the vector v. x1, y1. I don't know if that's a unit vector or not. Okay? All I know is I have a vector v. And what I'm going to do is scale it by the reciprocal of its magnitude. So I'm going to take vector v, and I'm going to scale it by the reciprocal of its magnitude flipped. So that, think of that as being distributed to each term. So you'd have 1 over, I'm sorry, let's write it like this. x1 over the magnitude of v, because you're scaling it by the reciprocal. So when you do that, the magnitude is it's in the bottom. And then do the same thing up here. multiply this to that. So you're going to end up with y1 over the magnitude of e. So you take each component and divide it by the magnitude. Or you could say multiply by the reciprocal. That's the same thing. But that is your formula. And that's what I've written down right here. You're going to take your vector, and you're going to divide each component of your vector by the magnitude. And when you do that, that's going to produce vector u. And I'm using u to stand for a unit vector. Okay, so the first step to finding a unit vector is figure out the length of the vector that you have. If you already have a vector that's 1 unit long, you're done. It's already a unit vector. If it's not, then follow this formula to divide each component by the magnitude, and that'll turn it into a unit vector. Okay, so let's try this one. It says find the unit vector that corresponds to 3i minus 4j. What, I drew a picture of this kind of earlier. What's the magnitude of 3i minus 4j? Yep. No, that one's going to come out to a nice answer. It's similar. I don't know if it's similar to one I had right there. I know that was +3, +4, and this one is -3, +4, but or -4, +3. Still the same thing. Yep, 5. So the magnitude of that vector is going to be 5. So, do I have a unit vector right now? No, why not?
Because the magnitude's 5.
Yeah, magnitude's 5, and
So
it's supposed to be what?
Uno.
1. So what do I need to scale the vector by to turn it into a unit vector? 1/5. So each component of my vector is going to get divided by 5. So what would be my new vector when I turn that into a unit vector? Yeah.
Would it be 3 over 5 and -4 over 5?
So 3 over 5 and -4 over 5. So what we did is we created a version of our vector that's 1/5 the size, points exactly the same way, but because it's 1/5 the original size, and the original vector was 5 units, the vector is 1. That's it. Any question on how we found our unit vector there? All right, so last thing we will take a look at is a special kind of vector that I did mention yesterday, and it's a velocity vector. So when we write a vector for velocity, what is the 2 things that the vector needs to tell me? If it's describing the velocity of an object. Yeah?
Distance and speed.
It's describing the speed, so it's definitely telling me how fast the object is going. And what's the other thing? Direction. So it's describing the distance, the direction and the speed. All right, so we're going to see if we can come up with a formula for a velocity vector. What they're going to tell you in a problem, you don't have to write it yet because we're not here yet, but they're going to tell you the angle that the object is being thrown at, and they'll tell you the speed of the object. Now, when we write a vector, is there an angle anywhere in the notation for a vector, whether we do it this way or that way? Is there an angle in there?
No.
No. So I'm going to have to show you what we do with that angle to make our vector look like the way we're supposed to write it. Vectors are not written with angles. Okay, so we've got to work with that. All right, so here's an example of a vector. And this would be the angle that they give you. The angle that they tell you is always going to be the angle that the object makes with the ground. So if they say an object was thrown at a 30-degree angle, that means it was thrown up from the ground at 30 degrees. What if an object was thrown at a 90-degree angle? What would that mean? Straight. Yep. The angle that the object is going to be thrown at, for our purposes, is always going to be somewhere between 0 and 90. 0 would be perfectly straight in front of you. 90 would be straight up. Okay, when we write a vector, we write it like this. What does the number in this box represent?
Would be X.
Yeah, X, which is the
Horizontal movement?
horizontal component. Yep. And what about the number in this box? Yep.
The vertical component.
The vertical component. So we've got to break down this vector into a horizontal and a vertical component. And what shape do you think we're going to create to make that happen? Any guess?
Repeat the question.
So what shape do you think we're going to create in that picture to break this vector down into its horizontal and vertical components? Because right now the vector is on a slant. We need to break it down into a left-right and an up-down. Kind of like the I's and J kind of thing. Yep.
Triangle.
Yeah, we're going to make a triangle out of it. So what I'll do is make a vertical. That's longer than I need, but that's fine. And where would be the horizontal component of that vector?
Ground.
Where?
The ground.
Yeah, on the ground. This is the horizontal component in purple. And where would the vertical component be?
The line you drew.
The where?
The line you drew.
Yeah, that's up to that tip of the vector. So what we need to figure out is a formula for the purple. That's going to go in there. And a formula for the green. That's going to go in there. So we're going to break it down into the purple vector and the green vector based on the information that they give me. Okay. Let's call this X, and we'll call that side Y. Let's start with figuring out the purple. What's going to go in this box? We're going to use this, and that. What trig function would involve the three things that I have circled? Figure out the positions of those sides and figure out which trig function has those positions in it. Yeah?
Cosine?
Cosine. Yep.
Oh, we're coming back to cosine.
Okay, so cosine of your angle equals, what's the definition of cosine? Yeah?
Adjacent over hypotenuse.
Adjacent over hypotenuse. So our adjacent is x. Now, what I know it's over the hypotenuse, but what specifically about the hypotenuse? The what of the hypotenuse?
Magnitude.
The magnitude of the hypotenuse, yes. It's not over the vector. If you put it over the vector, you would literally be doing this. That's the vector. The vector is a picture. It's not over the picture of the vector, it's over the length of the vector. And the symbol we use for that is magnitude. So any question why it's not the bottom one? That you can't have a picture in the bottom of a fraction like that. So now we're going to solve for x. How would you get x by itself there? Yep.
Multiply by the magnitude.
Multiply by the magnitude. That is the formula that goes in the first box. So if I tell you the speed at which I'm throwing an object and the angle that I threw it at, to figure out your horizontal component for that information, that's the formula. It's the speed times the cosine of the angle you threw it at. Now, let's, one more time, you gotta do it to find the vertical component. This time, use the angle, use the vector, and solve for y. What trig function would we use that involves the three things circled in green? Yep, sine. Sine of theta equals opposite over, and it's opposite over hypotenuse, but again, what of the hypotenuse? The magnitude, not a picture of the hypotenuse. Nope, don't want a picture. We want the length of it. Just like that. So what would we get when you get y by itself there? Yep.
Sine theta times magnitude.
Yep. I'm just going to put that in the front. Magnitude v sine theta. So if I tell you the speed at which an object is being thrown and the angle it was thrown at, take the speed times the sine of the angle, and that will tell you the vertical component of the vector for the information that I gave you. Okay, so those are the two things you need to find. Okay, so putting it, I can write it all together if you want to see it without arrows. So a velocity vector looks like this. Magnitude v, cosine theta, comma, magnitude v, sine theta. That is how you write a velocity vector.
Is it always going to be cosine of sine?
And it always has to be exactly in that order. Cosine is always used to calculate the horizontal. Sine is always used to calculate the vertical. So a lot of what we do in a lot of what we do with vectors and all kinds of other stuff, it always comes back to just finding the length of a side in a triangle, whether it's using Pythagorean theorem or whatever we have to use. It's usually all about finding something in a triangle. Okay, and I think I wrote down I can copy it over to this page too if we want. But it's the same thing we just wrote. So if I give you the initial speed and the angle, use that formula to find the velocity vector. Theta is the angle. And the magnitude of v is the initial velocity. that example. So let's figure out the last one. So it says the object, in this case, is being thrown 50 miles per hour at an angle of 30 degrees. Find the velocity vector. They do say to write the answer in unit vector form. Well, that's fine. This is not unit vector form. But if I just take that and put an I after it, and then take that and put a J after it and get rid of the comma and the brackets, well, then it can be a unit vector form. All right. So let's start with the horizontal. What's going to be the formula that we use to calculate the horizontal component? Mia, what do you think?
What was the question again?
For the we want to find the horizontal component.
I'm not sure.
Do you know what the formula is we're going to use? We don't have to plug into it right now. Just the.
Is it the one on the velocity vector one on the left? That formula?
Yep. And I just want the horizontal part of it for now.
So it would be the V thing and the cosine part?
Yep. Magnitude of v cosine theta. So now, can someone fill in the values from this problem into that? Oop.
For V would be 50, and then for theta would be 30 degrees.
So 50 cosine 30. That's the calculation for the horizontal component of the vector we're going to write. And we'll come back to that. What's the formula for the vertical? Yep. 50 sine 30. And we're going to round it. We'll just do 2 decimal places. So type in 50 cosine 30. That gives you 43.30. And 50 sine 30 gives you 25. So if we want to write the vector in this format, we just found each of those numbers. It's 43.3, comma 25. But they did ask for it as unit vector form. It's in the question. How would we write this as a unit vector? Yeah?
43.30I plus 25J.
43.3 I, it's supposed to look bold, plus 25 J. Okay, so that is the velocity vector. And the last part says to look at that and just explain the meaning of each component. Well, which component is this?
What was the question?
So which component is the 43.3? That's the horizontal component. So what would that mean in this problem? Like if this was actually happening, what could you measure and it would come out to 43.3? Yeah.
The distance traveled on ground, like in a straight line.
So this vector doesn't give us the distance. The I and the J are both components of the velocity, but they're not distance. Yeah.
The I would be the direction. And then the J would be the speed.
So the direction is 30 degrees. That would come from what they gave us earlier. The I and the J are similar, but they're not directions or distances. Yep. It's not directly the force, no. So remember, this is a velocity vector. And that 43.3 is a horizontal component. Yeah?
Is the j the height?
That would be like a distance.
Oh.
So no, there's no distances in that. All that stuff could be figured out somehow with some physics formulas and gravity. But these numbers are both speeds. Both speeds. But what would that 43.3 mean? No. Yeah?
Initial speed?
Well, the initial speed itself is 50 miles per hour. We got to be a little more specific when you say initial speed. Think about how we've broken the vector down. Yeah?
The speed it traveled horizontal.
It's the speed in the horizontal direction, yes. So in other words, if somebody were to throw an object at 50 miles per hour towards you at an angle of 30 degrees, you were standing right in front of it, and you had like a radar gun, and you pointed it at the ball coming at you, it wouldn't say the ball is coming at you at 50 miles an hour, because it's not. It's coming at you at an angle. The speed that it would come at you horizontally is 43.3 miles per hour. So that is the horizontal speed of the object. Not ignoring wind resistance, horizontal speed never changes from the time it leaves your hand to the time it hits the ground or whatever object it's going to hit. Horizontal speed stays the same all the time. Yeah, wind slows it down a little bit, like very, very little bit, especially for an object like a baseball. It's not like throwing a piece of paper. That wind slows that down a lot. So that's the speed in the horizontal direction. How about the 25? What would that be? Yep.
Speed in the vertical direction.
The initial speed in the vertical direction. So if you were in a helicopter over this situation and you pointed a radar gun straight down at the ball, the second it leaves the person's hand, with a machine throwing the ball, it would be coming up at 25 miles per hour. But that would only be for a fraction of a second because gravity is instantly going to start slowing it down. But the second it leaves the person's hand, it would be going 25 miles per hour upward. And then constantly slow down until it hits its peak, and then speed back up again on the way down. Okay, so any question how we got the velocity vector? Okay. So, let me double check. I think that's good. Same page as last night, 344. Yeah, so 55 and 57, those are velocity vector problems. And then the rest is all the different kinds of examples we did in class. Okay, so 25 to 47, that is just odds, not odd.